like Dan Margalit thought, he does not need an introduction. So it's lecture 2, reconstruction problems in mathematics.
Great. Thanks a lot, Victor. Thanks everyone for being here. I also want to say the conference has been great. I want to say a particular thanks for all the remembrances last night, everyone who spoke about Bob, well, during the conference and also at dinner. I agree, it's really important to know where we came from. And I also really find it inspiring to, try to live our careers so that people might talk about us like that someday. So unfortunately, I didn't know Bob, but I learned a lot about him yesterday, and so I appreciate that from everyone. A couple quick updates on the art on campus. I spent like 10 or 15 minutes with the knot. Who said it was the 2.5? Was that you? Yeah, the 2.5 Taurus knot. The knot in front of the Fubo building. I still can't understand it. So if anybody wants to stare at it with me later, we'll do that. Also, Noah and I were just walking, if you look to the right, when you go into the cafeteria, there's this huge triangulated torus. It's gigantic, and there's something happening on the inside, geometric, and I haven't figured out what that is. So if you want to look at that with me, I'm eager to do that as well. All right, well, let's get back to reconstruction problems. Yesterday was geometry, metric spaces. Today we're going to talk about topology, and tomorrow is group theory. So let's get to that. The title yesterday was bijections of metric spaces. Today is automorphisms of graphs, and in particular curve graphs. And I'll say what I mean by that as we get there. So the goal of the talk is to relate symmetries of surfaces to symmetries of graphs. And on the left-hand side, you should think something like a homeomorphism or a diffeomorphism. On the right-hand side, well, automorphism of a graph, you should think of as combinatorics. Okay, so we want to relate those two. Let me give you, I maybe should have mentioned this yesterday, but a kind of like an archetypical example of a reconstruction problem is the fundamental theorem of projective geometry. Somebody brought this up with me. Fundamental theorem of projective geometry. And Andy Putman has nice notes on this, and he credits this to von Staudt in the 19th century, so I tend to trust him. And the idea here is, I'm not going to do this in detail since it's not the main point of the talk, but the idea here is you have V is a vector space, and you assume that the dimension is at least 3, and then you have the poset of non-trivial proper subspaces. Okay, that's a combinatorial object. You can think of that as a graph. If you take the geometric realization, it has higher dimensional simplices as well, but it's really determined by the graph. And so you can ask about its automorphisms. And the theorem is that all of the automorphisms of this poset, or you can think of it as the complex, the geometric realization, the automorphisms come from, are induced by semi-linear maps of the vector space. Okay, it's a simpler way to say that is a linear map of the vector space will give you an automorphism of this graph, but also a field automorphism, give you an automorphism of this poset. So a semi-linear is just a combination of those two things. All right. That's right. Another example of one of these reconstruction problems where a linear map obviously gives you an automorphism of this poset, but here you're starting with an automorphism of the poset. You want to reconstruct a linear map, and that's that's how that goes. So if you know about this, maybe that's some inspiration. If you don't know about that one, you can kind of forget about it. But I wanted to make that connection. All right, so this post set is sometimes called the Tietz building. I wanted to switch back our focus to topology, and so in particular, we'll talk about surfaces today. So if you think of this post set as a building, I want to give you an analog for surfaces. Okay, and I want to give an analogous theorem to this fundamental theorem of projective geometry. Here, S is a surface. You should imagine something like closed surface of genus G, but it really can be any surface. And I'll define a graph, a curve graph. Okay, that's usually pronounced C dagger. And the reason is that there's already a curve graph without the dagger. And this is called defined curve graph associated to a surface. And the vertices are essential simple closed curves in the surface. Okay, now I have to be careful about what I mean here. The essential means not homotopic to a point. A simple closed curve is an embedding, topological embedding of S1 in the surface. And the important thing here is I only care about the image. Okay, I don't care about the parameterization. So these are unparameterized. So if I draw a picture like this, that's a vertex of this graph. Okay, I don't have to tell you where, how it's parameterized. Any picture like that is a vertex of the graph. So this is, of course, an uncountable graph because I can wiggle that curve any way I want, and that's another vertex of the graph. And so something like this is not allowed. That's homotopic to a point. And did I run out of colors? Ah, there's. And here's some other vertices. See. All right. So hopefully, maybe that's a little small. Tell me if you can't see it. The edges of this graph are just for disjoint pairs. Okay. So this big uncountable graph, the vertices are all the curves, the essential simple closed curves, and the edges are when they're disjoint. So you can see in this picture that this purple one, there's a purple, a red, and a blue and a green. And you can just see from the picture, if they intersect, I draw an edge. Sorry, if they intersect, I don't draw an edge. And if they're disjoint, I draw an edge. So let's see, red was just disjoint from all of them. And the green one, everything's there, I guess, except for the green and the blue. But of course, I've drawn, tell me if I made a mistake. Of course, I've drawn only a tiny piece. It's a big uncountable complex. It's locally infinite and locally, did I mess up somewhere? Okay, tell me if I did. So that's the object. We're going to want to understand the automorphisms or symmetries of that graph. Any questions on the definition? Yeah, of course.
I guess another way you can like build a graph for surfaces, like triangulations.
Yes.
Have you considered that?
So do you mean a graph in the surface or a graph associated to the surface?
Graph associated.
So you want a vertex of your graph to be a triangulation of the surface? I see. Yeah, that's right. That's something else you can do. I think that's hasn't. So that would be like a. I haven't studied that. I don't know if anybody has. I think that's a great question. You can make a graph where the vertices are topological triangulations of the surface. Maybe edges are like flip moves where you remove an edge and or remove a, yeah, maybe something like that. I think that's a great idea, but I don't know if anybody's looked at that. These graphs were introduced in a few places. Benson, Farb, and I worked on them, and originally we didn't write a paper. He gave a talk on it that's on YouTube, and then a couple of years later, Bowden and so Webb studied these, and what they were interested in is the group of either homeomorphisms or diffeomorphisms of a surface. Those groups are known to be perfect, and they use this graph to show that diff of a surface is not uniformly perfect. Okay, meaning so every element is a product of commutators, but maybe you need many, many commutators to write a specific element. And I won't go into that for this talk, but this is the tool you use for that, to get that algebraic consequence. All right, so that is the object we're going to study. Let me I'm going to call this classical, but it's really like 2017 or something like that. There's sort of 3 stages to the talk. I'm going to tell you what Benson and I did in the mid to late 2010s, and then I'll tell you what how I extended that with a group of RU students after that, and then tell you some really exciting work, which is work that was done by Catherine Booth, my graduate student. Yes. Okay, so I want to give a little bit of a preview before I get there on Catherine Booth's work, so you have something to look forward to. It's something that should be of interest to especially the geometric topologists in the room. Okay, so this is what we're going to build towards. So suppose I have a map of R2 to R2. If you want, you can say it's a bijection. You can even say it's a homeomorphism. And let's say I tell you that it takes every smooth curve in R2 to another smooth curve in R2. No corners, right? So it's the image of the smooth embedding. And maybe the inverse also takes smooth curves to smooth curves. What do you think you could say about such a map? Well, there's an obvious answer. You'd hope that would be a diffeomorphism. And so the answer turns out to be more interesting than that. And so that's the thing we're building to. So that's a basic geometric topology question that when we were first talking about it, I thought, oh, we can just open up SPVAC and there will be this lemma. But it turns out to be a lot richer than that. So that's the thing we're building towards, the basic geometric topology question. But I'm going to start with this, I think, even more basic question about curves on surfaces. Okay, so what we looked at, this is Benson, Farb, and me, is we looked at what's in retrospect called the extended fine curve graph, where you include the inessential curves. Oops. Okay, so this is a bigger graph. This is a graph that contains the previous one. And we studied there's a natural homomorphism. There's a natural map from the homeomorphisms of a surface to the automorphisms of this graph or the other graph. Okay, the E is for extended, which I guess is confusing because we're not adding the essential curves, we're adding the inessential curves. The E is for extended. All right, so there's a natural map. A homeomorphism of the surface takes curves to curves, it preserves disjointness. And the question is, this is a lecture series on reconstruction problems. The question is, is there a map in the other direction? This is similar to the fundamental theorem of projective geometry. It should feel like a hard thing to have a map in the other direction, okay? Because you're taking all the curves in the surface, you're permuting them, and all you're remembering is whether or not they intersect. Okay? That's combinatorial data. How are you going to get something like a homeomorphism of the surface, which is topological? One way you can think about this is if you were building some IKEA furniture, and instead of having the instructions of how the things fit together, you're just told which pieces touch which other pieces. Okay, that's all the instructions you're given, and told go put this together. Okay, that's kind of what we're doing here. There are some analogs of this. If you've heard of the curve graph without the word fine, where you're looking at isotopic classes of curves, there's an analog of this by Ivanov, which maybe would give you hope. But the theorem that we proved is that this is an isomorphism. I'll call this natural map eta. Eta is an isomorphism. In particular, there is a map in the other direction. Every automorphism of the graph comes from the obvious place, namely a homeomorphism. Again, there's three parts. This is just the first part. So any questions on the statement? Feel free to interrupt anytime. Okay, so let me tell you the key idea. Let me ask a question here first, which kind of embarrassed I don't know the answer to, but the isomorphism here is just as groups. Both of these are topological groups. Homeo has the compact open topology. There's lots of topologies you can put on this, and I don't know what the right topology is so that you get an isomorphism of topological groups. Okay, obviously you can just take the topology here, push it forward through the isomorphism. But so the question is, what is the right topology on the automorphism of a graph for this particular graph? So it's an isomorphism of topological groups. The first one or two obvious things you would try don't work, so I don't know a good answer to that. All right. Yeah.
Is another way to ask that question if you can already push forward the topology on Romeo? Is it just saying what other known topologies are identical to the push forward topology?
Yeah, exactly. You want to describe this topology in terms of something like, two automorphisms are close if they agree on some large ball in the graph. Something that's just purely combinatorial having to do with your graph. Yeah, that's the idea. Yeah, I mean, another way to say it is just push this topology forward and describe it in graph theoretic terms. I think it's a good problem. Okay, so let me tell you the idea for the key idea for this. And that is convergent sequences. Okay, we didn't invent convergent sequences, but I think we did invent convergent sequences of curves, maybe. I don't want to oversell this result. Part of the reason we didn't publish this is that it's probably something we could all figure out if I just, made this kind of teaching is that, I don't know, active learning classroom. What's that? Yeah, we could spend the rest of the hour. You guys could probably prove this, but I'll give it away. Spoil the. Convergent sequences. So let me say what that is. So I have a sequence here. C1, C2. It's a sequence of vertices of the extended fine curve graph. Somewhere, those are vertices. I don't know where to put the zero with the parentheses. It's going to be too much. Is convergent. It's a convergent sequence. If it converges, if the curves, these are vertices, if the curves converge, this is kind of a tautology, to a point in S, in your favorite topology. So they're shrinking down to a point. Okay. So if you want, you can say Gromov-Hausdorff topology. So the picture you should have in mind is C1 is this, and C2 is this, and C3 is this, and C4 is this, and C5 is this. Okay. So I'm talking about a sequence of vertices of the graph, but you can take those vertices of the graph, put them in the surface, and ask what they look like. And so this is why we're looking at the extended curve graph. I can't do this unless I have these inessential. These have to be inessential curves. They're converging down to a point.
So does that mean that the essential curves are like discrete?
Well, what do you mean by that? So they can't
get close to it.
Oh, they can get close to each other, but they can't converge to a point. Now, notice a point isn't a vertex of the graph, right? So, yeah, so it's some way we're trying to use the vertices of the graph to detect a point in the surface, right? Even though the point in the surface isn't in the graph, I'm using these to detect the point. It's kind of like the germ of a point. You can think of it that way. Yeah. So you have to use what you're given, right? We have an automorphism of this graph. We want to understand points of the surface to get a homeomorphism, but we don't have access to the points. We have access to sequences of curves, and that's our way of accessing the information we're going, right? That's how reconstruction problems work. You're trying to like build more and more data. All right. And so the key lemma, that was the key idea. So maybe I shouldn't call this a key lemma. The main lemma is that automorphisms of the graph, extended fine curve graph, preserve convergent sequences. Okay, convergent sequence of vertices. So you have this big infinite graph, right? A convergent sequence is a sequence of vertices in the graph. It doesn't look like anything, right? In the surface, it looks like this, but in the graph, it's just a sequence of vertices. And somehow, an automorphism of the graph can take one subsequence to another subsequence, right? You're staring at the graph, these convergent sequences don't really look like anything, but they do. That's the point. Any questions on that statement? Yeah.
Do you have to keep, is this only for like closed surfaces? What if you have like punctures?
No, this is fine. Yeah. This is fine. You'll see from the proof. Yeah. So sequence of curves converging to a puncture is not a convergent sequence. So, all right. So here's the proof. The sequence is convergent if and only if. So on the left-hand side here, the notion of convergence is topological. And so what I put on the right-hand side has to be information that's detected by the graph, right? So I'm trying to make a dictionary between, I just erased it, the symmetries of the surface and the graph. Okay, so everything I write on the right-hand side has to be something you can see in the graph. That way automorphisms will preserve it. All right, so the right-hand side says for all vertices A and B that intersect infinitely many CI. Okay. Intersect is something I can see in the graph. There's no edge. So for all A and B, so I've got this sequence of vertices, the CIs, for any A and B that are not connected to infinitely many of them. Okay.
And A and B are curves?
Yes, they're vertices of the graph, so they're curves. Thanks. A intersects B. Okay. Those are graph theoretic things. So it's hard to draw a picture of this in the graph, but the CI is some sequence of vertices. Those are the CIs. I don't know how maybe they're connected by edges, maybe not, but that's my sequence of vertices. And I have two other vertices, A and B. They intersect, so that means there's a non-edge. I'm going to draw a non-edge as a dotted line. So A intersects infinitely many of the CI. B intersects infinitely many of the CI. Those are non-edges. Then there's a non-edge between A and B. Okay, that's the picture. So a graph automorphism will preserve that because you can see that picture. Okay, and there's a for all in the stage. Okay, the proof of this is pretty easy. It's a pretty easy topology exercise. Let's draw the picture. So here's my here's C1, here's C2, here's C3. They're converging down to a point. And let's see, A is supposed to be a curve that intersects infinitely many of them. So it's going to have to go through that point in the middle that these curves are converging to. And so B is also going to have to go through that point. And so A and B can't, whoops, I missed. So A and B, A and B can't, must both go through that point. So they're not disjoint. So you've translated something on the surface to something that's not pretty to look at, but it's something that's in the graph. And so any automorphism has to preserve a picture like this. Well, there's a for all in here. Also, it's for all A and B. This is true. Yeah.
Why can't these CIs not be converging, there being space in the middle, where so that A and B miss each other?
That's right. So that's because it's so which direction am I proving? I'm assuming that they,
This way.
yeah, you want to go the other way. Right. So why is it? Right. So for the other direction, maybe the picture looks like this. Maybe they don't go all the way down to a point. They go like this, right? They sort of, I don't know if that's clear what I'm doing. I'm limiting to this circle. Is that your idea?
Yeah, and the A and the B somehow don't touch, they kind of.
That's right. But this is good. So this means what you have an example here where the curves are not convergent, and I found an A and a B that don't satisfy this. Okay. Yeah. So that's right. Now, so yes, you have this. Yeah. The forward direction is this picture. The reverse direction takes a little more thought, but it's not harder. It just you have to get the quantifiers in the right order. Does that make sense, right? Yeah. All right. Any other questions? That's it. That's the proof. Oh yeah.
And I guess with the notion of like sequences, why like orbit finite many practical.
Oh yes, that's right. You can cut off the beginning of the sequence. So in a convergent sequence, they're all inessential. But yeah, we don't. Yeah. But I can't. But I can't see that in the graph, right? I just have this graph. I can't see just by looking at which ones are essential, which ones are inessential. But I can see this. Okay, so it follows from all this that after some point they're all inessential. Okay. So I want to use this word that kind of came up in my head when we were talking over there. So these convergent sequences are a proxy for a point, right? You're trying to reconstruct, what is a point in the surface? I've just got this graph. I want to reconstruct what a point. What do I mean by that? Let me say what the end of the proof is. Is this? By the way, this is the same thing we did yesterday. Remember yesterday we took a point on the boundary of hyperbolic space and we characterized it by this fountain of geodesics that came out of that point, right? And we wanted to get a map on the boundary. We said, well, take a point on the boundary, build its fountain. The image of that fountain under the bijection is another fountain. And so you take that point on the boundary to that point on the boundary. We're doing the exact same thing here. Right there, we use the fountain as a proxy for a point at infinity. Now we're using convergent sequences as a proxy for points in the surface. Okay, so I'll just give the key point of the proof, which is building a map. Oh, I'm using building in a different way. Building a map from automorphisms of EC plus S to homeo. So what does this mean? You're given a phi in here, okay? And then you're given a point in S. So let's say we have phi in here, we're trying to make an F in here. We want to define an F of X. This is to me the confusing thing if you're seeing this for the first time. So we're trying to go from an automorphism of the graph to a homeomorphism of the surface. So given a phi here, we're trying to build an F here. And so that means given a phi here and an X in the surface, I need to say where it goes. I need to say where every point in the surface goes. Okay. And again, it's the thing we did yesterday. You just use the convergent sequences as proxies. So, so let CI be a convergent sequence converging to X. Okay. Then the lemma says that the phi of CI is a convergent sequence to some point Y. Okay. And so you just set f of X equals Y. That's it. So that gives you at least a function. Well, it's not obviously a function, right? Because what if I choose two different convergent sequences for the same point? I have to show this is well defined. But you do that, and it's not too hard. And so now we have a function from S to S. It's invertible because the automorphism was invertible. You check that. And then why is it continuous? That's the key thing. It's continuous almost by its nature, right? These CIs converging this point are giving an open neighborhood of the point. And so you use that to argue open neighborhoods go to open neighborhoods and vice versa. I won't do the details, but I trust that you could do it. Okay. But the key point is just constructing the map. And again, just like yesterday, using proxies. That's it. Any questions? Yeah.
Does well-definedness follow from, like, suppose you have two convergent sequences going to the same point, you kind of glue them together into a single larger.
Exactly. Yeah. Right. Yeah. Two convergent sequences. Yeah. That's not how we said it, but I like that way of saying it. Two convergent sequences glue together to give you a convergent sequence. You just interleave them. Yeah. Any other questions or comments? So that is the first one. I am going to now move, again, I'm stealing from Olu's technique. What's that called? Or a rhetorical technique. I'll call this the neoclassical. This is maybe, is this after COVID? This is like 2022 or something, maybe 2023. I understand there was math before 2016. I'm just as a rhetorical technique. Okay. Okay, so this is work with, oh, I guess I cannot say that. Now, Yvonne Verburn, who was a postdoc at Georgia Tech with me, co-led this project with 3 undergraduates, Adele Long, Anna Pham, and Claudia Yao. And we looked at a different version of this question. And the version we looked at is this. Looked at the natural map. The original fine curve graph. So hopefully you feel like me, like that's, I mean, I like that, it's nice, but it's also kind of cheating. Once you have the inessential curves, I don't know if cheating is the right word, but once you have the inessential curves, you have this really nice characterization of a point. The much harder version is when you don't have the inessential curves. All the curves are essential. You just can't do that, okay? So the question again is, of course, can you make a map in the other direction? And of course, the problem is the only tool we have is out. And this already came up in conversations. Right? We can't have essential curves converging to a point. So we have no tools. Okay. I'm going to describe the strategy here. The strategy is sometimes called the tea kettle principle. Which is a very fancy way of saying something simple. I learned this, yeah.
I might be missing an assumption here, like if a contractible surface,
Yes.
then what about the graph? It's like one point, right?
Yeah, so let's take this to be a closed surface of genus G. Yeah, so right, we want the graph to be non-empty. Thanks. Any other questions? When I was teaching at the University of Utah, I taught a math class for poets. I don't know what you call it, but it was just like students who really didn't want to take math, but they had to still require. And we used Spivak's Hitchhiker's Guide to Calculus, which is an awesome book. It's like a little like comic book kind of thing, but it's great. And he tells, this joke in there, which I think has been around for centuries. And the joke is like, first you ask a mathematician how to boil some water. And they say, oh, you take the tea kettle's on the table, I guess. You take the tea kettle off the table, you fill it with water, you put it on the stove, you turn on the stove. Okay, they wait for it to boil. And then the next day, the mathematician comes in and the tea kettle's on the stove full of water. And you ask the mathematician, how do you boil water? And they say, well, you dump all the water out, put it back on the table so that you've reduced it to a known, problem you already know how to solve. So anyway, that's a very long-winded way of saying I'm going to reduce this problem to one I already know how to solve. So, but it's amusing. So, whatever. All right. So the idea here is we're trying to get a map from the automorphisms of this curve graph to homeo. But what if I can just do this? So this is my tea kettle on the table, which I already know how to get from there to homeo. Yes. So in the extended fine curve graph, I have these convergent sequences, which give me proxies for a point on the surface. Now in here, I need a proxy for an inessential curve, right? So that I can say what happens over here. That's the idea. Okay, so we need a proxy in the fine curve graph for inessential curves. So you can't use the same kind of technique, right? You want to say, oh, I'll take a bunch of essential curves that converge to an inessential curve, but that doesn't work because they stay essential. You have to do something kind of different. Questions on the setup here?
Is the arrow from ought C dagger to ought EC dagger supposed to be an obvious?
No. Yeah, that's right. Yeah. So this is the question. So let me explain this sentence again. So you're given an automorphism of this. Now that's permuting all of the essential curves of the surface. You want to get an automorphism of this. So you want to permute all the curves on the surface. Well, you already know what to do on the essential curves, right? This automorphism tells you. So to go from here to here, you need to tell me what to do with every inessential curve. Here's an inessential curve. Tell me what other curve to send it to. Okay. And to do that, I want to somehow see, just like in the previous one, we could see a point in the surface from some collection of vertices here. I want to be able to see an inessential curve here by some collection of vertices here. And I want to have a proxy again. Okay. Hopefully it'll make sense when I say what the proxy is, but any other questions, what we're trying to do? Okay, so the proxy is easy to describe. I won't be able to give you the full proof for this one. Okay, so let's see, here's part of the surface. Again, I'm thinking of a surface of genus, actually genus at least 2. And I have, red and blue make purple. Okay, here's my inessential curve. Okay, I want to find something in the fine curve graph that detects that. Here's what I do. I take this red curve here. Okay, it's exactly agreeing with the purple on the top half. And you can see what I'm going to do next. I take this blue curve, which is agreeing with the red, but I'm drawing it separately just so you can see it. And it agrees with the purple down here. So the red and the blue agree, except they just do a little blip like this. Okay, and then keep going. The picture is a little hard to see because there's 3 colors all overlapping, but any questions on that? So the main lemma is that automorphisms of the extended, no, sorry, of the fine curve graph preserve Lygon pairs. So given that lemma, let's, if you want to call this epsilon, proceed as usual to find epsilon. What do I mean by as usual? Right? Given an automorphism here and an inessential curve here, you need to say where it goes. Choose a bygone pair where the bubble is that inessential curve. See where the bygone pair goes. It goes to another bygone pair. That gives you another inessential curve. The problem here is it's not a quick one-liner like it was last time to show that automorphism preserves these. It's a sequence of like 9 or 10 things. I'll give you an idea of what goes into it. But it's even harder here to show well-definedness, right? There's many bygone pairs for that inessential curve, right? I can wiggle the red and the blue. I can send them around different places on the surface. And so it's much less obviously well-defined. So that's a lot of work. I'll give you a quick idea of what the first steps are. This is a really quintessential reconstruction problem. So automorphisms of fine curve graph preserve. So if I were to write everything out, there would be a sequence of 9 or 10 steps, and at the end, we'd say they preserve Lygon pairs, so pairs of curves like that. The first one is that they preserve separating curves. Well, let me say it in the other order. It makes sense for a curve in a surface to be non-separating, right? It doesn't divide the surface into 2 pieces. Because the automorphism is bijective, it would follow that an automorphism preserves separating curves just by using the inverse. And also the sides of a curve. Meaning, well, that'll become clear as I explain it. Okay, so I'll hold on to that. Okay. So the proof of this, so I'm proving that an automorphism of this graph preserves separating versus non-separating. So I need to find a way in the graph to encode separating and non-separating. So a vertex of the graph, which is a curve, C, is separating if and only if the link of C is adjoined. I'll define join in a second, but it's a graph theoretic term. Let's look at a separating curve in a surface. This idea goes back to Ivanov and maybe earlier. Once you see the idea, it's so simple. So I want to show that an automorphism of the graph preserves that this curve C is separating. Well, I have, let's call them the AIs on the left, all the curves on the left. There's uncountably many. I have VIs, they're not countable, but VIs on the right. Those are all connected to each other in the graph. They're all disjoint from each other. That's what a join is. You have two subsets of a graph, and everybody over here is connected to everybody over here. That's what a join is. And that's just clearly what you have here. So you have to maybe argue that for the other direction, that if you have a non-separating curve, oh, what's the link? The link is all the vertices connected to a given vertex. So here's the vertex C. The link is everything connected to it. Notice the AIs and the VIs are exactly the curves connected to C, right? They're the ones disjoint from C. And it makes a join because everything on the left is connected to everything on the right. And so, so this is a very compact way of saying that. And then you have to maybe argue the other direction. If you have a non-separating curve, you can't divide the link of C into two pieces where everything over here is connected to everything over here. I'll let you think about it. So this is at least some kind of topology. And you start with just an automorphism of the graph. You got some kind of topology. I'll just say you go from there. I wish I could keep going, but I think that's all I have time for that part of the talk. But any questions on it? Yeah.
I have one quick question. Is there any way, or has it been done, like a formulation of this in terms of like the cohomology, the co-cycles?
Of what? Of the graph or the?
Or of the curves? Is there any sort of
Oh, well,
of,
yeah, being separating is the same as being trivial in cohomology, so you could phrase it that way.
okay.
I
I don't know if there's any benefit to that necessarily.
don't know of one. I mean, it's always useful to think of it that way, but I don't know of a good way to use that here. It's a good question.
So
Yeah.
your idea is to like make bygone pairs to make an inessential or essential. Like
It's not making it, it's making an essential curve out of, it's making an inessential curve out of essential curves, right? It's kind of like you're encoding. So if it's true, so a bygone pair is any pair of curves that looks homeomorphic to this picture, right? If it's true that automorphisms preserve those pairs, then what I mean by proceed as usual, right? So given automorphism of all the essential curves, you need to get an automorphism of all of the curves. Okay, so I need to say, given this, where do I send this inessential curve, right? So I take that inessential curve, I draw a bygone pair for it. The automorphism over here takes it to another bygone pair. That's a new inessential curve. So I've just said where to take that inessential curve to. Not, well, obviously well-defined, that's some work, but that's the idea. You're just trying to find a way of encoding the vertices here that aren't here. So we're using vertices here to encode the vertices, the extra vertices here. Other questions or comments? Okay. I think I'll stop on that and go to the next, the Catherine Booth work, which I wanted to tell you about. But I'll just say there's lots of other questions here. Like, so we're understanding homeomorphisms of a surface from the automorphisms of a graph. You could ask about what does a covering map look like in terms of maps of graphs? What does a rational map of the sphere to itself look like? What does a branch cover look like? There's many other questions. I'll hold off then. All right. So now I'll go to the modern, which is the last couple of years. This is my student, Catherine Booth. She was a student at Georgia Tech and is going to University of Chicago for a postdoc in the fall. So, all right, so what she looked at is C1. Sorry for the notation. This is the smooth, fine curve graph. Okay. So this was supposed to be a nice, simple thesis problem. Show that the automorphisms of this graph is diff of S, right? What else should it be? Okay, so there is a natural map. What eta again? From diff. Well, or you could say C1 maps of S. It depends what you mean. Maybe that's your definition of diff. So I just mean one's continuously differentiable homeomorphisms to the automorphisms of the smooth fine curve graph. But you know what? I need to emphasize what this means, or even say what it means. So what is a smooth curve in a surface? So it's the same kind of graph. The vertices are smooth curves, edges are disjointless. So what is a smooth curve? A smooth curve is a curve with a smooth parameterization. But it's an unparameterized curve. Okay, it just has to have a smooth parameterization. If this is my surface, I can't see this. That's a well-defined thing, right? You have smooth structure on a surface. I can tell whether there's a corner or not. Okay, that has no smooth parameterization. X sine 1 over x has no smooth parameterization, so you can't see that. So smooth curves just look smooth. It might be the same as locally flat. Someone in the audience can tell me that. Is that right? It feels like locally flat. Yeah. Oh, corners locally flat. Oh, in this, I see. So it's, never mind, I said anything. It's recorded. Oh, yeah, okay. Sorry, I thought it was smooth. Kind of every ground. Yeah. Okay. So, again, the old tools are out. Because if you look at the bygone pair picture, that's very not smooth. Okay, you have to make the curves turn, right? You can't make all three of them smooth. You can try for a second and you realize it doesn't work. So I'm going to write down the question I said at the very beginning. Given f just from R2 to R2, I know I'm mostly thinking about surfaces of positive genus, but let's just look at R2. And f preserves smooth curves, and maybe f inverse also preserves smooth curves, is f a diffeomorphism.
Allowing inessential curves again because you're in R2.
Yes. So this is yes. So it turns out a lot of the subtlety for this problem has to do with the local picture. Okay, and so this is something you would expect to see in Spivak calculus, or at least in Spivak's differential geometry, right? I think we spent quite a bit of time just searching the literature, trying to find that yes, this is a characterization of a diffeomorphism of R2. And it turns out that the answer is an emphatic no. And a lot of her work has to do with understanding this. So I'm going to try to tell you a little bit about it at the end of the talk here. That's surprising, I think. That's still kind of okay. So let me convince you that the answer is no by showing you the LaRue-Wolf example.
Sorry, what is the notation of that superscript?
Which superscript?
Plus minus.
Oh, sorry. That's f plus or minus 1. So I'm going to not only tell you that f preserves all smooth curves, but also the inverse. So it's just so you don't think that's the issue. Okay. So here's what they do. They give you an f from R2 to R2, where R theta maps to R, I don't know, some other function. So we're looking at a map from the plane to the plane. I'm not going to change the radius of any point. I'm just going to change the angles. Okay. And I'll take H to be smooth. I think that's needed. Odd. Okay, I'll explain that in a second. But the key, those are the technical points. The key point is that H of 0 is 0. H of pi over 2 is pi over 2. And H of pi over 4 is not pi over 4. Okay. What's the picture here? So picture is, I mean, what does a smooth curve look like? You can imagine you're zooming all the way in. So a smooth curve basically looks like the y-axis, the x-axis. I could just take the x and y-axis as my smooth curves. So those curves under this map, since I'm not changing the angle at 0 and pi over 2, this map is going to take those and basically fix them. Okay, more or less. Okay. But what does it do to this curve that comes in like this? It's going to move it one way or the other. Okay? The oddness tells me that whatever angle it changes up here, it's going to change by the same angle down here in the other direction. Okay. So you can make a diffeomorphism like this. Just take H to be nice. So it's a diffeomorphism of R2. Sorry, it's not a diffeomorphism. That's the whole point. It's a map of R2. It's a homeomorphism of R2. Why is it not a diffeomorphism? Did anyone see the punchline there? Yeah, what's going on with the origin though? It's definitely at the origin.
The identity.
Yeah, well, it should be the identity, right? If this was a diffeomorphism, it would have a derivative at the origin, which would have to be the identity, right? Because you're fixing the x and y axes. But if it was the identity, it would also fix the line y equals x, and it doesn't. Okay? But it's taking smooth curves to smooth curves. Every smooth curve, when it goes to the origin, basically looks like a line, right? You zoom in enough, it looks like a line. And so it's preserving tangent directions, but it's not linear. So that's their example. Any questions on that? I think that's just, yeah.
Do you at least get that F is always like a continuous map?
Great question. So that's one of her theorems. So let me tell you her theorem. Her theorem is that the automorphisms of the smooth fine curve graph, or maybe that's not smooth, maybe that's the C1 fine curve graph, whatever you're calling it, is a subgroup of homeo. So it does come from a continuous map. But we just saw, just because you can do this local picture on a surface of genus whatever, we just saw that that the diffeomorphisms are a proper, or C1 maps of S are a proper subgroup. So somewhere in between. So it's some weird group that she calls homeo 1. So it's a new subgroup of homeo. So this is just the automorphisms of the curve graph are homeomorphisms with some that preserve smooth curves. So these two things are the same, but this is emphasizing it's some new subgroup of the homeomorphism group of a surface. And I'll just to end, I'll give you an idea of some of the mysteries around this group. And there's many questions, many mysteries. And I'll just give you a couple. One, homeo 1 is not contained in homeo 2. I haven't told you what homeo 2 is. Those are curves that have a parameterization that's twice differentiable. Okay, You should think of that as like the osculating circle varying continuously. Okay. So you can have a homeomorphism that preserves C1 curves but doesn't preserve C2 curves. I know it's bizarre. Some people are upset. I'm sorry. Number two, there exists F such that F preserves C1 curves, but F inverse does not. Okay. The way she does this, she finds a homeomorphism of the plane that squeezes x sine 1 over x to something differentiable. Okay, and the inverse does the opposite. It takes something differentiable to x squared, x sine 1 over x. And I'll give you one more. There's elements of homeo 1. So these are homeomorphisms that take C1 curves to C1 curves with an accumulating. Oops. The word accumulating is accumulating on the other column, with accumulating non-differentiable points. So in these examples, you make it not differentiable at a point, but you can put lots of non-differentiable points. That's the time we have. So let's say one last thing, which is, I don't have time to write them all down, but there's many questions about the group homeo 1, the group's homeo k. It seems like this rich direction that might be of a special interest to geometric topologists. So I'm happy to talk about it more, but thanks for listening. I appreciate it.
Okay, so we'll leave, time for questions. You can go ahead and harass Dan during lunch. So now we'll go ahead and reconvene here again at 1:30. But I want to go ahead and while everybody heads up for lunch, take a short little detour and kind of show you an exhibit that's just a couple minutes walk in this direction, called The Roots of Knowledge. It's a massive stained glass exhibit that showcases the history of human knowledge. Now, I warn you, it's a lot to take in. I said so. I mean, of course, keep in mind that you should get some advice to eat and everything like that. After you get a bite to eat, you can continue and stare and then take it all in. So we'll head over there and then we can go ahead and go for lunch. Yeah.
Is there a local characterization of homeo?
Great question. Yes, you have one of her papers. Gives a local characterization. It's not easy to say what it is. It's anything you try. Well, she gives a great talk on this. You think, oh,